Kia ora, Year 12 and 13. This is question 1A from the 2010 Scholarship Calc paper. It's a complex numbers question. And question 1A usually seems to be a bit of a warm-up, so this one is not too bad. In fact, you could do this if you were just revising for level 3 complex numbers. So the question is to a proof to show that this complex number, z equals cis 7 pi on 11, is a solution of this equation here. Remember that cis theta is shorthand for cos of theta plus I sine theta, right? And that's when we're using what we call polar form to write complex numbers. Now, if you're watching this video, you hopefully should know all of that already. If you're in my class this year, we haven't actually done this yet, but you'll figure it out as you go. So this is theta, okay, and if we put in r here, r cis theta, this is saying that we have a modulus, or a distance from the origin to that point, of r. Okay, now as soon as we see an equation with complex numbers raised to powers, we need to use a fantastic bit of maths called de Moivre's theorem. De Moivre was a French mathematician, and I suggest, again, if you're watching this, you're probably going to find it quite interesting to go and look him up and see all of the amazing maths that he discovered. So this theorem links complex numbers with trig, but he also did a whole lot of interesting work in probability, including one of the first steps towards the central limit theorem. Anyway, back to this one. We're going to substitute this into here, and we're going to apply this theorem, his theorem, which I haven't put down here yet, which is that if we have this complex number to the power of n, it simplifies to give us this. Right, so we'll just start by substituting into the left-hand side and seeing where we get to. So z to the 19 plus z to the 14. So I'm not going to talk much, I'm just going to write. Okay, so we're doing this to show what we're doing, even though it feels kind of like we want to show whoever's reading it that I'm starting out by substituting in like that. Now we're not writing equals 0 because we're showing that it equals 0, so we're just going to keep on working on the left hand side. So it's just like when we did trig proofs earlier in the year. So next step is to apply this theorem, and we're going to simplify these. Now just notice that r in here is equal to 1. So if I just have 1 cis theta to the n, that equals cis of n theta. So my expression now is equal to 133 pi on 11 plus cis 98 pi on 11, and so on. Now you might already be looking at this and going, oh, that doesn't look much better. It certainly doesn't look quite like 0. But what you have to remember is that when we're working with complex numbers, this is theta here, so theta starts at 0, and as we move around to 2 pi, we're going to double back up. So cis of 0 is equal to cis of 2 pi. We can knock out multiples of 2 pi in here, and that's what I'm going to do now. So looking at 133 pi over 11, that's equal to cis of 132 pi over 11 plus pi on 11. The next one, 98, is equal to cis 88 pi on 11 plus 10 pi on 11. Now I know I'm going to run out of room. Now the next one, 56 pi, don't be tempted to go to 55 because we're looking for multiples of 2 pi, and we're going to have a negative theta, right, which is an angle down here. Again, if you've done complex numbers, this should feel pretty straightforward. If you haven't, you'll probably get the feel of it from this anyway. So that's that one there. And then the last one, 21 pi, is going to be plus cis 22 pi on 11 minus pi on 11. Lots of you watching this won't need to will be able to skip through this a little bit to the next step, but you need to make sure that you show that you're taking out multiples of 2 pi. So this is quite a nice line to put in. So now that equals cis of 12 pi plus pi on 11 plus cis of 8 pi plus 10 pi on 11 plus cis of 6 pi minus 10 pi on 11 plus cis of 2 pi minus pi on 11. Right, now we can just rewrite that with the basic angle in there, right? So cis of pi on 11 plus cis of 10 pi on 11 plus cis of negative 10 pi on 11 plus cis of negative pi on 11. Now I'm going to split out the real and complex bits, remembering that cis of theta is cos theta plus I sine theta. So I'm going to do that now. So first we're going to have cos of pi on 11 plus cos of 10 pi on 11 plus cos of negative 10 pi on 11 plus cos of negative pi on 11. So that's the real part. Plus I times sine pi on 11 plus sine 10 pi on 11 plus sine, I'm running off the edge of the screen here, I'm sorry, hopefully you'll get the idea, plus sine a negative pi on 11. Right, pretty illegible, but you should be getting a feeling for what to do for the next step, because we're going to use a couple of ways we can do this, but even in odd functions it's going to make this really easy. Okay, so we know that cos of x is equal to cos of negative x, right, just from our basic trig. Now, what does that mean? Well, it means here that we've got 2 lots of cos of pi on 11 plus 2 lots of cos of 10 pi on 11. We know that sine of x, so the real part equals that. Now let's look at the complex part. Well, negative sine of x equals sine of negative x, because sine is an odd function. It's a shocking sine wave, but there you go. Okay, so now if we look at the complex part, again on a new slide, we've got I of sine pi on 11 plus sine 10 pi on 11, and we had plus sine negative 10 pi on 11 plus sine of negative pi on 11. So we can rewrite that as I times sine pi on 11 minus sine pi on 11. So that's that bit and that bit gone. And the same thing plus sine of 10 pi on 11 minus sine of 10 pi on 11. So that's that and that gone. So we've got rid of the complex part. So now we're down to showing why 2 cos, where was I? 2 cos pi on 11 plus 2 cos pi on 10 pi on 11. So we're back to working with the real part. So that complex part was 0. But if we just take another look at our trig graph, we can see that here's 0 and here's pi. Cos of theta is equal to negative cos of pi minus theta. In other words, cos of pi on 11 up here is equal to negative cos of 10 pi on 11. So this equals 2 cos pi on 11 plus, oh, really have to go to a second slide for this. 2 cos pi on 11 plus 2 cos 10 pi on 11 is equal to 2 cos pi on 11 minus cos minus 2 cos pi on 11, since cos pi minus pi on 11 is equal to negative cos pi on 11. So that equals 0. So we've shown that the real part equals 0 and the complex part equals 0. Now, if I were writing that out, I wouldn't split them out and write the real part and the complex part. I'd just keep going. But it's just getting too long to do on the slides. So what we've shown is that z to the 19 plus z to the 14, in this case, plus z to the 8 plus z cubed equals 0 when z is equal to cis 7 pi on 11. In other words, this is a solution of that equation. Alright, so for many of you, I'm sorry if that was a little bit too slow, but there are just lots of little applications of things that you already know from level 3. So thanks for watching, and if you find any mistakes or anything's not clear, please just leave me a comment.